Hello, uh, welcome. Today, I wish to produce a video about two different topics. And let's see here. I share screen, and here goes. First thing I want to show is that all non-empty vector spaces have a basis. And the second thing is when we give an example about this theorem, we want to give you an elementary example of a vector space that has an uncountable basis. Now, this video is aimed more at undergraduate level. If you need a little refresher, well, I think since I'm going to be basically outlining the proof, I'm not going to be proving every detail, it shouldn't be too tedious for you. So let's start off with one. Show that all non-empty vector spaces have a basis. So let V be a vector space. That's non-empty. Okay, so it's not empty. Now, the very first thing you can do is, since the V is not empty, there exists X. So let X be a vector in V. So let's call this X1, a vector. Now, if V is going to be the span of X, we're done. Of span of X1. So suppose not. So then let V sub 1 equal the span of X sub 1. But because V sub 1 is not equal to V, we're going to let X2 be not in the span. Well, let's just do this here. Let X2 not be in V1. So then you do the same question. So if the span of X1, X2 equals V, we're done. If not, let V2 equal the span of these two vectors. X1, X2. And continue. Now, this is technically an induction kind of operation, because what you're really going to be doing is that you're going to be repeating this process possibly infinitely often, possibly an uncountable number of times. So basically the way this works, so as you continue on, you let V sub alpha, where alpha is some ordinal. No, all ordinal is like 1, 2, 3, 4, omega 1, omega 0, which is the first countable ordinal, etc. But if you're just learning, all it is an ordinal is something that orders something like first, second, third, as opposed to a cardinal, 1, 2, 3, etc. So let V sub alpha equal the span. And so you've done this construction. And by the way, for the new students, yes, there's a way of well ordering this, but let V sub alpha be the span. And if V sub alpha is not equal to V, there is some X alpha plus 1 not in V sub alpha. Now, the reason why I'm doing this, and this is where it gets a little dicey here, there are such things as limit ordinals. Now, what a limit ordinal is an ordinal that has no predecessor. Now, a finite number like 1,000, well, there's 999, and so it has an immediate predecessor. But if this is, say, the first countable ordinal, there's no immediate predecessor to it. There's no infinity minus 1. So for the first uncountable ordinal, every predecessor will be finite. So you might have to repeat this process for the so-called limit ordinals. but there's an immediate successor. So you can't talk about alpha minus 1, but you can talk about alpha plus 1. So let this not be in there, and let v alpha plus 1 equal the span. Now we're going to start at x1 and go all the way out to x sub alpha plus 1. And just continue. And you continue as much as you can. So we have vector subspaces. And again, a possible infinite chain. V1 contained in V2, contained in V3, all the way out to say V alpha, insert V alpha plus 1. That continues onward without bound. Now, this is for new people, this is going to be where we get into the axiom of choice. There's a theorem of mathematics called Zorn's lemma. Depends on the axiom of choice. And what Zorn's lemma says is that given any ascending chain that with an upper bound, in fact, I'm phrasing this terribly. I'm phrasing this terribly here. So let's get rid of this given part right here. That was clumsy of me. But any ascending chain with an upper bound and I'll explain what that means in a second, has a maximal element. Now, and let's call that V. So in this case, let's call it V star. Now, what maximal element means is that this maximal element means that every V alpha is going to be a subset of that, but there is no element in the chain. Let's call it V prime, where V star is a subset of V prime. So it has a maximum element. Now, in this case, our chain here of all these spans, of all these vector subspaces, all of these lie inside the original vector space. So our chain has an upper bound. So has a maximal element. V star. Now, there's two things I have to do. So first of all, I need to show that this V star is equal to V. So one, suppose our V star is not, and better make this, be careful here. Suppose this is not V. Has to be contained in V. Then there is a vector, let's say X star, where X star is not in V star, but it's in V. So we take V star, and when we union with the span of X, or we take V star, well, in fact, I'm being clumsy here. So what I'll do is I'll take V star and append to it the span of X star. And this contains V star. In fact, this union here is actually a very, very bad way of writing it. I want to be a little bit better than this. So I'll just write it as a direct sum. And this contains V star, so V star is not maximal. That's a contradiction. So that's the first thing. So we've arrived at a contradiction here. Okay. So our V star has to be all of V. Now, two, I have to show that x1, x2, x3, x alpha, let me just continue on, are linearly independent. So, how do we do that? Now, I want to change color here, but the big deal, what's a big deal here is that note vector addition is finite. Because remember, when we have this, with vector addition is in fact finite. This we're not really allowing for infinite sums here. Now I realize some vector spaces can have a notion of an infinite sum. For example, Hilbert space, but then you need to add a notion of limit. The actual vector addition thing, though, is in fact finite. So given that that's finite, what we can do is we can choose vectors. So let's say, suppose x sub alpha 1 plus x sub alpha 2 plus x sub alpha k, some finite number, times alpha 1 times alpha 2 all the way out to alpha k. Let that be the zero vector. Now notice these alpha sub i's are not necessarily finite ordinals, although these numbers are finite because these are all scalars. In fact, I realized I kind of screwed this up here. This is what happens. I'm right before I'm a little bit sleep deprived. These should be different numbers here. I really messed this up. So let's just get rid of this junk here. They shouldn't be the same number because they're not. These are just some scalars. So I'll just put these in a different color. Let's see here. All right. All right, come on now. All right, so let's make these blue, I guess. And let's go ahead and make this say beta 1, because these I don't want you. These are not the same. Let's say this is beta k. So these are just scalars corresponding to these ordinals, which may or may not be finite. But there's only a finite number of them because vector addition is finite. So this is only a finite sum. And you can order these so that, because these are ordinals, you can order them like this. So we assume this. Because vector addition is commutative, so you can order it in any way. So I'm going to order it like this. So now, by moving this, we can say that beta 1 x alpha 1 plus beta 2 x alpha 2 plus beta n k minus 1 x alpha k minus 1 is equal to minus beta k x alpha k. Okay, we can do that, not a problem. And then just by doing a little division, we get minus beta 1 over beta k beta 2 over beta k x alpha 2 da 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 plus beta k minus 1, and these are all assumed to be non-zero. And I should have said that. I should have said that. Got a little bit fancy here, but this assumes that beta 1 not equal to 0, beta 2 not equal to 0, etc. So these are all non-zero. So what this means that this x sub alpha k is in the span. Which contradicts how the subspace was built. Because remember, every time you added another x sub whatever, that was by definition not in the span of the previous ones. Well, if you had this zero relation here, this thing, x of alpha k, where alpha k is a higher ordinal than all the rest of these, and yeah, and I should have said right here, x sub, that this is going to be in the span, and that's a minus 1 here. So we get that. So in fact, this vector is in the span of these, which contradicts how we built our subspaces up. So we can conclude this labels us to say that every non-empty vectors, every non-empty vector space has a basis. Okay, so that's a mouthful. Now, let's just do an example. Now, and again, this is assuming that the person taking it is doing their first linear algebra course. Now, you've probably seen an example. So let's do the example of polynomials. Now, the polynomials with a let's say real coefficients. That's an example of a vector space. You know, the sum of two polynomials is another polynomial, et cetera, et cetera. And I'm assuming, of course, finite degree. Although there's no limit to the degree, you can have a polynomial of degree 10 million or 10 trillion or whatever, but it's still finite. So the way this particular thing works is you start off the vector 1, would be the vector x of 1, x could be the vector x2, x squared could be the vector x3, and the buildup would be, what we just did here. And this exhausts itself in a countable number of steps. Okay, so in this case, your V would be all polynomials. And if you notice, since there's no limit, this is what's known as a vector space that has a countable basis, but every predecessor to the countable ordinal is finite. Okay, so that's something to see here. So polynomials, they all have finite degree, but there's no limit to the degree. That's an example of a vector space with a countable basis. Now here's one that's uncountable. And this is actually not a bad vector space at all. With an uncountable basis. This would be the following. It would be the vector 1, and then the vector e to the alpha x, where alpha is any real number. So this would be a basis for the vector space. This is going to be our basis. So our basis, now in theory, there's something called the well ordering theorem. So technically speaking, you should be able to list every single one in some sort of weird order, but that order has nothing to do with how we actually count the real numbers. So it's a colossal mess. But our basis basically is basically the collection of these things and our vectors. So it's with alpha equaling 0, that gives us a 1. And our vector space will be the span of all e to the alpha x. Now, it's easy. So I described the vector space. It's just what all linear combinations of these, for example, would be 1 plus e to the 2x plus e to the square root of 3x plus e, let's say, to the pi squared x. And let's put it a 3 there, and let's make that a 5, and etc. Be things like that. Now, the question is, how can you prove, or how can we prove that, how can we prove the following fact? That if, let's say, alpha 1 not equal to alpha 2 not equal to alpha 3, so if you have any k real numbers that are unequal, in other words, these are k distinct numbers, so that if we have this, then the vectors e to the alpha 1, e to x, e to the alpha 2, x, e to the alpha kx are linearly independent. How do we do that? Now, if you've had a course in differential equations, you might know what's coming next. So here's how we do that. So what we do is suppose, like before, beta 1 e to the alpha 1 x plus beta 2 e to the alpha 2 x plus beta k e to the alpha k x is equal to 0, where all the alpha 1, alpha 2, alpha k are all different. So suppose you have that. Now here's what we're going to do. So if this is the case, we're going to do a little calculus. So now if you differentiate both sides, so you take d dx of both sides, you take d dx of this, of 0, well, derivative of 0 is 0. Well, what we get here is we get beta 1 alpha 1 e to the alpha 1 x plus beta 2 e to the alpha 2 x plus, and by the way, the bi's are all non-zero, of course. Differentiating both sides, this must be 0. And you can do this. And what I want to do is I want to create k different equations. So this is the first equation. This is the second equation. You can continue to differentiate. So do the second derivative. Well, the second derivative gives you this. And this gives you an alpha 2 squared. This gives you an alpha k squared, bk e to the alpha k x. And if you do this k minus 1 times, what you get is a following matrix equation. And this is kind of cool here because what you're doing, this equation, you get a 0. This equation, you get a 0. This equation, you get a 0. By writing this in matrix form, what we get is 1, 1, and you get k of these. The next one you have alpha 1, alpha 2, all the way out to alpha k. Alpha 1 squared, alpha 2 squared, all the way down to alpha k squared. And you keep going down until you get alpha 1 to the k minus 1, alpha 2 to the k minus 2. Alpha 2 to the k minus 1, alpha k to the k minus 1. Multiply by b1 e to the alpha 1x, b2 e to the alpha 2x, all the way out to beta k e to the alpha kx. Now, this is where we use a linear algebra fact. This matrix here has a special name. Now, what I'm going to do, I'm going to stop share for a second and go to this, and we'll say what the proper name is. It's Vandermonde. So let's go back to this. Vandermonde. So let's go back to share screen. Vandermonde. And I got that from, as you can see here, that is the name of the matrix. Vandermonde matrix. By the way, I highly recommend the Wikipedia article on this matrix because that's a Vandermonde matrix. Now, and let's just call this M. Now, if we can show if the determinant of M is not equal to 0, this has only, miswrote that, has only the 0 solution. So that's kind of neat here. So I want to go ahead and share this. Save this. Matrix 1. And let's go to a new one. So that's what we like to do. So we need to show that this Vandermonde matrix is non-singular. Now, how do you do that? They're non-singular if all alpha I are unique. Now, how you'd actually do that, and this is where I'm going to actually sketch the proof, and I also recommend the Wikipedia article. I'm going to do this in an inductive way. So let's assume, let's start with the 2 by 2. Let's assume we have 1, 1, alpha 2, and where alpha 1 is not equal to alpha 2. Now, by the way, so I should want to say note, this is the Wronskian matrix. If you had some differential equations, this is a Wronskian matrix for e to the alpha 1x, e to the alpha 2x, etc., evaluated at 0. But anyway, let's get back here. So assume these are not true. So if you take the determinant, we get alpha 2 minus alpha 1, no problems, okay? So it's true for 2 by 2. I'm not going to worry about the 1 by 1 case. 1 by 1 case is just 1. So assume true for, in fact, what I'm, so assume it's true for up to k minus 1 for some k. We already know this is true for k equals 3, because we just proved it here. This is actually k equals, shoot, so this would be k equals 2, right? So we've already shown it's true. Shown it's true for k equals 2. So now let's just go up to k, 1, 1, 1, all the way out to here. And this goes to alpha 1k, alpha 2k. Let's see if I'm being consistent here. So let's see, 1 to k minus 1. So I have k rows and k columns. That's good. All right. So this would be k plus 1. So this is our matrix here. Now, this is what we do. I'll demonstrate, I won't do the complete tedious proof here, but I'll demonstrate the technique with, let's say, something like a 4x4, so it's a little bit easier to follow. And when you apply the same operations that we're doing here to a 4x4, you'll see what's going on. So now I guess I'll go ahead and just do it this way. So the very first thing you do is you take row, in this case, this is the k plus first row, and you replace this by row k plus 1 minus alpha 1 times row k. Now what happens here? Well, in this case, and let's be careful here. The first few rows are not affected. But look what happens here. You have this is going to be alpha 1k minus alpha 1 times alpha k minus 1. Well, we know what that is. The next one is going to be alpha 2k minus alpha 1 alpha 2k minus 1, etc. And then right here, we're going to have alpha k plus 1 minus alpha 1 as to the kth power, the k minus 1 power. Now look at that bottom row. This bottom row right here. The bottom row looks like this. Well, here you get a big fat 0, and that's good. Now let's look what happens here. Let's factor out an alpha k minus 1, and I have an alpha 2 minus alpha 1. That's good. Keep this up. What do you have? You'll have an alpha k plus 1 to the k minus 1 times alpha k plus 1 minus alpha 1. That's what you have in that particular row, bottom row. So the bottom row, what we did is we got a 0 right here, and then we have everything that looks like this. So the next thing is we work on the k plus the kth row, and we place the kth row by r k minus, same thing, alpha 1 times r k minus 1. Now I'm going to go a little fast here, but now look at when we do that, 1, alpha 1, where we already have a 0 here. We get a 0 up here because alpha 1, well, we get that. Down here, we have alpha 2, k minus 1, alpha 2 minus alpha 1. Well, when we do this, what we're going to end up with is we're going to have here, you're still going to have a factor of alpha 2 minus alpha 1, but this is going to be alpha 2 to the k minus 2. Now let's do the multiplication to see that that's right. That's your k plus 1, and that is your alpha 2 k plus 2 times this. And that happens in every column up to here. This is alpha k minus 2 k plus 1. And so what we do now here, and notice what we have this common factor in this column. We have this common factor in this column. So we repeat until we end up. So we repeat this for every single row. The next step, the next step would be rk minus 1 would be rk minus 1 minus alpha 1 rk minus 2, etc. So if we repeat that carefully enough all the way to the very last one, we'll have a 1 here. These will all be zeros. This one, we'd have an alpha. In this very first one, we'd have alpha 2 to the 0. So we have alpha. That's just a 1. So we'll just get rid of that. We'd just have a alpha 2 minus alpha 1. The next one would be an alpha 2 minus alpha 1, all the way down to alpha 2 k minus 1. And the same thing here. We'd have an alpha k plus 1 minus alpha 1, alpha k plus 1 minus alpha 1 times alpha to k plus 1 to the first power. And we would have all the way down to here. I'm sorry, these are alpha 1s here. So you have this matrix. Now, there's a fact about matrices. The determinant of this matrix, well, notice you have these 1s and you have all these zeros. So basically, it's basically going to be this, it's going to basically be the determinant of this matrix here. But every element of this column is multiplied by alpha 2 minus alpha 1. So it's alpha 2 minus alpha 1. Then the next column is going to have a factor of alpha 3 minus alpha 1. And again, each element of this column has this factor. And remember, if you multiply a column by a matrix by the same number, you take the determinant of that is the same thing as multiplying that same factor by the determinant. So and then it's going to be the determinant of this minor here. And what minor do you have? Well, you have a 1, all the way out to here. You have an alpha 2, alpha 3, all the way out to alpha k plus 2. And this goes down to alpha 2 k minus 1, alpha 3 k minus 1, da da da. But this is where the induction comes in. Notice these are all the products of alpha 2 minus alpha 1, alpha 3 minus alpha 1, alpha 4 minus alpha 1, da da da. So we do the same thing here. And the determinant is Well, here you got alpha 2 minus alpha 1, alpha 3 minus alpha 1, all the way out to alpha k minus 1, k plus 1 minus alpha 1. Then you have the same thing going on here, but now you have your alpha 2. So it's alpha 3 minus alpha 2, alpha 4 minus alpha 2, all the way out to times the determinant of the next minor. And the next minor is going to have a bunch of ones, etc. But now this is going to be alpha 3, alpha 4, etc. And this gets reduced. So basically, but we've already, this has one row, this has one dimension less than the previous matrix. So by the induction hypothesis, you can calculate the determinant of this matrix like that. So what the total determinant turns out to be, because you do the same thing again to calculate this, and then the same thing to calculate that down till you get to a 2 by 2. So what the determinant will be, and this is how it's usually phrased, it's going to be the product, and it's going to be 1 less than or equal to I less than j less than or equal to, in this case, let's go to the very last one. It's going to be k plus 1. And it's going to be the alpha j minus alpha I. So basically the product of all possible differences of these, where the first one is higher order, is one further in the order, it's further in the order than this. So that's where this j greater than I is. And this is equal to 0 only when some alpha I is equal to alpha j and I is not equal to j. Otherwise, the matrix is non-singular. In the language of differential equations, the Wronskian is non-zero. So what this proves that e to the alpha 1x, e to the alpha 2x, etc. are linearly independent if alpha 1, these are all not equal. And there is your, now to complete the proof that this is actually uncountable basis, and this is what I'm not going to prove here, this we assume the reals are uncountable. And that's a pretty much an established fact of mathematics. So that's what I have on this. It's a little bit rough, but thanks for watching.